To the presentation on this paper titled A Survey on Image Data Augmentation for Deep Learning. The paper has been authored by Shorten and Khush Guftar. My name is Usman Hassan. The contents of the presentation. As for introduction, basically in data augmentation, we extract additional information from images that may be based on occlusion, lighting, and viewpoint, etc. A deep learning model is called generalizable if the performance it gives on training data does not significantly drop on the testing data. Otherwise, we say that the model has overfitted the training data. So when we do data augmentation, we are basically making our model more generalizable. In contrast to some other techniques that focus on modifying weights, data augmentation focuses on extracting more information from the original data set. So this paper presents a survey of image data augmentation methods and their suitability for different computer vision applications. So we can see that broadly speaking, image data augmentation can be categorized as basic image manipulations and deep learning approaches. And recently, a new concept, meta learning, has been introduced wherein a network is trained using another network. Okay, so let us first consider basic image manipulations for data augmentations. So the first method for basic image manipulations is geometric transformations. Uh, we can see that in many data sets, there may be positional biases present. For example, there may be all the faces perfectly centered in a data set. So it makes it difficult for those faces to be recognized if they are position translated in the test set. So what we can do is we can do translation, cropping, rotation, and flipping to add to our training data set. Cropping, rotation, and flipping transformations, they might not be label preserving if employed beyond a certain threshold. Color space transformation is based on the notion that we eliminate color biases present in the dataset in favor of spatial characteristics. Overly bright and dark images make it difficult to recognize objects of interest. So what we can do is we can do augmentation via thresholding and histogram manipulation to mitigate this problem. However, a word of caution here that if we convert an RGB image into a grayscale image, it does not improve classification accuracy. Rather, it has been shown to reduce classification accuracy. Hence, if we want to transform an RGB image into another space, we may go to SSV space, etc. And color space transformations may not be label preserving if important color information is lost. For example, if an image contains blood in red color and we manipulate red color beyond a certain extent, then in the transformed image the blood may not be visible. Okay, another interesting method for basic image manipulation is sample pairing. So in this figure, we can see that we have two images, image A and image B. They have been randomly picked from the training set, and then we extract patch A from image A and patch B from image B, and then we mix their intensities. We perform average intensity of two patches, and then this mixed patch is given the label same as of image A, and we feed this mixed batch into our training network. So this method of sample pairing has been bring significant improvement in validation, and it has also been observed that the greatest reduction in validation set error occurs when the candidate images when the candidate images A and B for sample pairing are selected from all the classes. If A and B are selected from the same classes, then also there is some reduction in validation error, but not as much as it would be if they were selected from all the classes. Okay, let us come to the deep learning category. So within deep learning category, we have feature space augmentation methods. So in feature space, we have output of a middle layer of our network available, maybe in form of vector. And what we do is we expand this space instead of contracting the space inside our model. A very popular feature space augmentation method was presented in a paper in 2017 whose architecture is shown below. So we can see on the left we have a sequence autoencoder, and what we do is that we feed our examples into this sequence autoencoder, and the encoder's hidden state at the final time step is called the context vector C. Okay, so then in the middle image we can see that we have fed two images into sequence autoencoder, and we have obtained their context vectors C1 and C2 for example, and then we can perform data augmentation based on interpolation, noise injection, or extrapolation. In this particular paper, the authors talk about doing interpolation based on k nearest neighbors. So we synthesize a new context vector C prime based on k nearest neighbors of C, J, and Ck. And now the resulting context vector C prime, it can either be used directly as a feature for supervised learning, or it can be decoded to reconstruct full sequence for training a sequence classifier as is shown here. A disadvantage of feature space augmentation is that it is difficult to interpret the vector data, for example in context of a convolutional neural network. Okay, but we can use an autoencoder network to recover the new vectors into images. How about that? But the autoencoders required for this purpose will be massive and time consuming to train. Okay, so the next method is adversarial training. So let us talk about the concept of adversarial attacking. Adversarial attacking consists of a rival network that learns augmentations to images that result in misclassifications in its rival classification network. So the authors refer another paper that shows that 71% of images can be misclassified by changing just one pixel. Okay, but we can use this adversarial attacking phenomenon to our advantage. We can perform the adversarial attacking on our data, and we can see which augmentations are good. If augmentations are not expected to result in misclassifications, they are good augmentations and we can use them to augment our data. Otherwise, if augmentations they are resulting in misclassifications, we can leave out those augmentations. However, this method is applicable on the training set, not on the test set. It is not clear if it will bring reduction in overfitting. Still, they can improve weak spots in the learned decision boundary. Then we have GAN-based data augmentation. As we know, a GAN consists of a generator and discriminator, and with the help of generator, we can synthesize new data. There are many variants of GAN like DC GAN, cycle GAN, etc., which are used to synthesize data for various applications, for example, medical applications. The disadvantage is that the GANs themselves require a substantial amount of data to train. So let us cycle GAN based data augmentation. So first we understand what is happening here. We have two GANs. We have a generator A to B. This is generator G. So the real image of a horse is converted into image of a zebra B while preserving the contents of horse. And then generator F or generator B to A reconverts this fake zebra image into horse image. So what we need here is a new loss function that is called cycle consistency loss. As we can see that there are two blue spots here. So one blue dot represents the real horse and the other blue dot represents the reconstructed horse. Of course, our objective is to bring these two dots as close as possible. And finally, since we are using two GANs, so we have our second generator F available. Why not use this generator F in parallel? So this GAN, the second GAN with generator F, can take real images of zebra B, and this zebra, the real zebra, will be converted into a fake horse while preserving the features of a zebra. And the first generator of the first GAN, that is generator G, we may say, will reconvert this fake this fake horse into a zebra. And there will be another cycle consistency loss here, which I have not shown. This cycle consistency loss will be based on the difference between the real zebra and the reconstructed zebra. So how can it be, this network be used? This network can be used, for example, in translating majority classes into minority classes. If we have class imbalance problem in our data set, we can convert some majority classes into minority classes by using cycle GAN. And this cycle GAN architecture has been shown to improve accuracy by 5 to 10% in emotion recognition applications. Finally, we have meta learning, and in meta learning, the research is still going on. One method is known as neural augmentation. So the augmentation network is a CNN, and this CNN picks up two images randomly from the dataset and generates a new image, and that new image is now subject to a neural style transfer. And finally, from this third image, the loss function is generated. However, this neural augmentation method, as we will see in the next slide, has not been shown to bring accuracy across a range of experiments. The report in dogs versus goldfish classification problem, the neural augmentation method gives 90% accuracy, which is good. But in cat versus dogs classification, the neural augmentation method gives 77% accuracy, which is in fact lower than other techniques. And with MNIST dataset, this neural augmentation method does not bring any effect on that. Okay, finally, we have to keep in mind some design considerations. We can do test time augmentation. If test image is augmented in the same way as the training images, then prediction can be made robust. Test time augmentation has reduced highly confident but incorrect predictions on medical image segmentation. In medical images, if they are we are doing it offline, and it is okay, but for real-time prediction applications, the test time augmentation method is a very costly bottleneck. Finally, we have to consider data size. If we transform data beforehand, it requires additional memory, and if we transform data on the fly, it results in slower training. So we have to choose one of these approaches based on our problem. So, conclusion. It is not clear for many data warping based and oversampling based augmentation techniques why they are effective. Representations learned by neural networks for GAN based augmentation are difficult to interpret, and further evaluation is needed of test time geometric transformations and test time neural style transfer augmentations.